All right. So as many of you are aware, if you are doing the CSLP summer reading program, the theme for 2022 is Oceans of Possibilities. So in that link bank that Beatrice put in the chat, we do have a collection of activities all about oceans and also some activities that have to do with oceans on other worlds. So be sure to check that activity list out if you're gearing up for summertime. But before we head into summer, we often like to give you library staff a backstage pass to some of the awesome science behind these themes. So that's why we are joined today with two subject matter experts to give you a look into what NASA is doing with our ocean and also other ocean worlds. And so to kind of give you a view of what's heading today. So after this welcome and introduction, we're going to do a quick little icebreaker as a poll question. Then we're going to go into other oceans worlds with Dr. Schenk. Again, definitely check out those oceans activities in the link bank. And then we'll end with Dr. Wood talking about sea level and ice in Greenland. We'll have plenty of time for questions and discussions today. Please share any questions that come up. Feel free to put into the chat. I will be monitoring that and we can get to any of those. But yeah, definitely be active in the chat, or you're welcome to use the Q&A function as well. That's in your toolbar. And we'll be sure to go back to any of those questions. So first, just a little thing to get us thinking about oceans. This is for our Earth, our planet, our ocean planet. How much water on Earth is fresh water? So I'm going to launch this poll so you can actually click right into the poll. And your options are 50%, 25%, 10%, or 3%. And I'll keep this up here for about 15 seconds for you to make your selection. All right, it looks like everyone has answered. So I'm going to end the poll and share the results. So we've got some mixed answers here, but if you answered 3%, you are correct. So of course, water covers 71% of Earth's surface, but most of that, almost all of that is salt water. And so we have about 3% that's fresh water, but again, even 2/3 of that is tied up in ice and glaciers. So the amount that's actually usable for humans is way smaller even than 3%. I think it's such a tiny number. I'm not even going to attempt to explain it, but yeah, only about 3% of our Earth is covered in fresh water. So we do have such a precious resource here. And that's why we need to learn about it and do our best to conserve when we can. So thank you for participating in the poll. And with that, I'm going to stop sharing and I'm going to turn it over to Dr. Schenk. And we're going to go outside of our planet and learn about what he's doing with other ocean worlds.
Thank you. Let's see. Let's have to figure out how to do this. All right, let's make sure everybody can see the screen.
Yep, looks great.
All right, let's launch into presenter mode. And I'm going to try to go through these quickly so that we have as much time for questions as possible. But what I'm going to basically introduce to you is the concept of ocean worlds in the solar system, because as you can see from the slide, I'm hinting that there's a few of them, and we're going to talk about several of these. And NASA has in fact set ocean worlds as an exploration priority because in the past 2 decades or so, we become aware that there are quite a few ocean worlds in the solar system beyond our own. But the main themes I want to touch on is what is in fact an ocean world? How do we know that they exist? And very briefly, in fact, rather briefly, why are they important? Now, obviously, we live on an ocean world. The importance of water to life should be pretty evident to us. Many species live in the ocean, and most of those who live on the land require water to live. There are a few exceptions to that, but most of them do. So what is an ocean world? Well, it's a world with an ocean. It may seem rather trite to say that, but we can define it in various ways. And one of those is to say that an ocean world should have a more or less contiguous global layer of liquid water of consequential depth on or beneath the surface. And on the Earth, that ocean is on the surface, but on the outer solar system, where the surface temperatures are very cold, bitterly cold, the surface is frozen, so that ocean lies beneath. Now, you would say that Earth's ocean is not complete, but it is global and interconnected, so we consider it an ocean world. Now, of course, what the meaning of consequential depends on the person making the definition, so we can talk about that at some point as well. Now, back in 1979, we thought only Earth had an ocean, and in fact, Mars is one of the most intriguing planets in the inner solar system. It has river channels and deltas and valleys and lake beds and evidence of a wet past, but it is now dry. The inference from all the geological evidence is that there was a large northern ocean on Mars long ago. In fact, you can map the shorelines of that ocean from geologic mapping of Mars from orbit today. In fact, we have several rovers on Mars that are examining the rocks to determine what the geochemical record of that ocean was and what it left behind. And we're going to be launching more rovers in the coming decades. But I'm not going to talk too much about Mars here because I don't study Mars. I study the rest of the solar system out beyond Mars and the asteroid belt. We have several large moon-sized satellites in the Jupiter system. We have 4 of them, in fact. And Voyager in 1979 found erupting volcanoes on Io. Io has no ocean or water on the surface, but it's been so geologically active that any water that was there has been basically boiled off. But Europa and Ganymede, we're going to talk a bit about Europa in a moment. And Ganymede both have outer shells constructed of water. And most of that water is frozen on the surface, of course, but underneath there are large oceans. There's something strange about Europa, and we're going to take a close look at it. These are some of the highest resolution views we have of Europa. Looks like basically broken up sea ice. And that's not a horrible analogy. It's not perfect, but it's actually not a bad concept because these show broken up plates of ice. And even though it's brown colored, we know from the density of Europa and from spectroscopy that the surface is composed of water ice. The geology tells us that there's probably a liquid ocean beneath the ice. It has an outer ice shell roughly on the order of 10 to 20 kilometers thick. Water layer underneath that's 75 kilometers thick. And if you total up the mass of that water layer, it's more water than we have on the surface of the Earth, which is why it's something of a compelling exploration target. We're sending a mission to Europa in 3 to 4 years. It'll take a while to get there, but we're sending it in 3 to 4 years. And as you can see from the high resolution image, it's got a very complex geologic record indicating tectonics and breaking up and all sorts of funny things going on. But you notice there's no impact craters on this surface. I mean, you can identify a couple. There's one down there, another one somewhere else, but it's very sparse. This is very different than the Earth's moon. Very young surface, less than 100 million years old. And we suspect that the water, because we have some insights into the interior, that the water layer is in contact with the rocky core. And that's important for geochemistry and whether or not anything inhabiting the ocean has nutrients to work with. But the clincher for the story was The Galileo orbiter, which orbited Jupiter in the late 1990s, had a magnetometer. And every time it passed Europa, it detected a very strange signal. And that's what these squiggly lines are for. And they show that the magnetic signature as the orbiter passed Europa was strongly disturbed when it passed by, indicating that there was an ocean beneath through magnetic induction. Jupiter has a very powerful magnetic field, much more powerful than ours. So as Europa goes through it, it disturbs that magnetic field. And it does so in a way that indicates liquid water is present in the interior. So we have a combination of evidence. One is all this activity and the youthfulness of the surface. In order for it to maintain that youthfulness, it needs something. It needs some sort of heat and activity in the interior. The magnetic signature indicates that there's liquid water underneath and therefore a source of heat. Cassini discovered something very similar at the smaller moon Enceladus orbiting Saturn, but it also discovered something Galileo did not at Jupiter, and that is active volcanic vents, if you will, of water ice spewing out of the south pole of this active moon. And Cassini actually flew through the plumes very safely, it was not a problem, with a detector that measured that it's mostly water, ice, crystals, with small amounts of salts and other phases. And those chemicals indicated that the water was reacting with the seafloor at the bottom of the ocean. There's other evidence for an ocean on Enceladus. One is that the shell is librating. And by libration, I mean wobbling. We know the orbital characteristics of Enceladus, and by the nature of the wobble, we can tell that the ice shell on the outer surface is actually floating because it wouldn't wobble nearly as much if it was stuck, grounded on the on the rocky core. So in order to wobble, it has to float, be free, decoupled, if you will. So a complex story, but it is compelling. This just gives you a cutaway diagram showing what we believe the interior to look like. A rocky core, probably some water bound in the minerals in the rocky core, but there's a global ocean underneath. An icy crust, again, due to the very cold temperatures, and then the active eruptions at the South Pole. The other examples include Triton. Triton is a large moon-sized satellite of Neptune. We've only seen this satellite once, barely cold temperatures again, 35 Kelvin. Evidence for internal activity and possible ocean include the extremely young surface, very few impact craters, maybe as little as 10 million years old on average. Very low topography, and that's something I was involved in directly. Extremely low topography, and in order to get that kind of topography, you need to have high heat rates, which can cause the ice to actually flow laterally and flatten out. Basically, like the surface of the ice sheet on Greenland, which we'll be hearing about soon. There's also extensive volcanic deposits, and this is a perspective view of some of those volcanic deposits. And by volcanic, I mean melted and brought to the surface, and you can have that happen in an icy crust just as much as you can have it here on Earth. There's also geysers that are erupting on the surface. You can see the plumes here and here formed by those. Since we only saw this once and we didn't have the best resolution, we don't know whether these are geothermal or due to solar heating, which is a compelling reason to go back to Triton. The key question is why we have these oceans, because it's so cold out there. Why didn't they just freeze? And the key to that question is media not found. Okay, I can't play it, but that doesn't matter. We'll proceed. Is tides, global tides, gravitational tides. We have tides here on Earth that cause the surface of the ocean to move up and down, but the difference here is that Jupiter and Saturn and even Uranus and Neptune are so large, so massive, that the tidal distortions on the bodies of these satellites are meters in amplitude, rising up and down. This is a lot of movement of the ice shell and the surfaces of these bodies, and it creates a lot of friction in the crust and in the crystals, interlocking crystals in those shells, generating huge amounts of heat, much more so than in the Earth-Moon system. And those are enough, if the conditions are right and the geometry of the tides is right, to actually induce melting and keep these bodies active longer than they would normally be. So gravitational tides are critical. And wrapping things up here, ocean worlds are found in many varieties. This is a short list of the bodies that we have confirmed or strongly suspect that there are oceans. They can be, the oceans can be a few tens of kilometers to almost 100 kilometers thick. Volume of Ganymedes Ocean, for example, is 6 times that of Earth in Europa. We suspect that there may have been oceans on these other bodies as well in the past. There's a remote possibility that some of these may actually have active oceans. I think evidence is moving Pluto up higher in the list, for example, maybe even Ceres. Most are covered by an ocean shell due to the very cold temperature, of course, which makes exploration challenging. Some of these oceans may be in contact with the rocky cores, as I've said, which means exotic chemistries, and we need to look at those more closely, but we don't have access right now. So what we need to do is develop means to get samples or to determine in some way what the chemistry of those oceans are, because we can't answer the habitability question without knowing what the chemistry is. And we have not been to the surfaces of these planets, ocean worlds. So we've set this as an exploration priority. These are some of the objectives that we have when we get there. I'll let you read those, and you can actually see in the diagram at the bottom a hypothetical cross-section of what these ocean worlds might look like if we could cut away and look at their insides. We know, for example, that plume activity is ongoing on Enceladus. So this is probably realistic for Enceladus. We know that there are diapirs, which is upwellings of solid ice on Europa, for example. But what's going on even deeper is even more mysterious. So we have that to look forward to, and I'll thank you. And I think we have time for a few questions at the moment. Is that correct?
Yeah, absolutely. Thank you so much, Paul. So if anyone does have any questions, please feel free to drop those in the chat. I have a question, actually. Could you talk a little bit more about what type of instruments are on the spacecraft that are used to study these other ocean worlds?
Yes. To date, we've only sent spacecraft that fly past these moons at several kilometers per second. And we have a camera on board, at least as a bare minimum. And the camera not only allows us to document the surface morphology and what features are there, fractures, volcanoes, whatever it is, but by using the camera in sequential, getting sequential photographs, we're able to get stereo images. And the stereo allows us to see the surface in 3D and consequently also get topographic maps. How high are the volcanoes? How deep are the fractures? That sort of thing. That allows us to characterize the strength of the materials and how much volume of material came to the surface, that sort of thing. That's the sort of thing I work on primarily, is topographic mapping. And Voyager did not have one, but Galileo and Cassini, New Horizons at Pluto, all had infrared spectrometers. And infrared spectrometers look at the infrared wavelength of the surface and look for spectral bands that identify what type of ice, because methane, even nitrogen, ammonia ices all have distinctive infrared signatures that allow you to identify them. And we look for where they're distributed. Are the volcanic deposits composed of water ice? Are they composed of ammonia ice? That sort of thing. Methane ice, as another example. We can also look at the distribution of those ices as a function of altitude. And that's something that was very fascinating on Pluto, where we have an atmosphere, for example. Titan, where we have organics. Those are the two main instruments that we've sent to the outer solar system. They're critically important. There are other instruments that look at UV signatures. The magnetometer detects the magnetic signature, as I described earlier. Cassini had a particle analyzer that determined what the composition of the ice grains that struck the spacecraft were made of. Cassini is the only one that's done that so far in the outer solar system, but there are plans to do that at Europa, where it'll be critical. Those are the ones I can think of right now. There are other instruments that provide useful information, but those are the key ones.
Great, thank you, Paul. And just to tie that back into one of the activities on that link bank, there's an activity called Investigating the Insides, where you can use models of other worlds that you put together and have your patrons explore them by using instruments such as magnets. The kids or patrons can start to make inferences off of their observations. So check that out on that link bank if you're looking to do an activity that's hands-on, that's related to looking at other ocean worlds. And we have a couple more questions in the chat here for you, Paul. Leah asks, what future exploration of ocean worlds is currently in planning stages?
The one that is currently in planning and actually being constructed now is Europa Clipper, which will go and make multiple flybys of Europa, the ocean world, the young ocean world orbiting Jupiter. And it will have, I think it's 13 instruments, including a radar sounder. This is the first time we sent a radar sounder, which will send a radio, or basically a radar signal to the surface and penetrate the ice, which is something we can do in Greenland, for example, and maybe Michael will talk about that, and see what the structure of the ice shell is, and look for evidence that the ice shell is overturning, or maybe search for pockets of ocean material embedded within the ice shell, and see what the history of that has all been. It'll obviously do it'll do global mapping, of course, and have a much better spectrometer on board. But perhaps one of the most important things it will do is look for activity, current activity, erupting plumes of ice material, ice vapor, that sort of thing, which we don't have any evidence for right now except from the Earth. So going there and seeing those up close and demonstrating that they're actually occurring would be critical. We have another mission that's going to Triton, which has an atmosphere as dense as ours, mostly nitrogen, and that will look for organic material on the surface by putting a helicopter, basically. Not as small or as simple as the helicopter on Mars right now, but much more advanced, and have instruments and measure compositions of various organic and non-organic materials. But it's an ocean world too that has methane rain on it. So it's a very interesting topic. So those are the two. There are other possible missions, but those are the two that are currently been funded to proceed.
Great. Thank you. And it looks like another question got answered by one of your responses. So the last question in the chat is, are there any practical plans for using this information, such as transporting the water or ice from some of these ocean planets back to Earth, since water continues to become more and more scarce?
That's a longer term question because the expense of going there, sending mining equipment, then mining the water, and then putting it on transports back to the Earth is so expensive that it would be impractical at the moment. But it'd be more useful as a resource for people going to explore those moons. Now, in the future, when we have an infrastructure in the solar system built, then it would be more practical. But right now, it would be prohibitively expensive to consider such options in terms of practicality.
Thanks.
And I can answer some of these in chat by
Sure.
typing in an answer. So if I've got one in the Q&A that I'm answering right now.
Oh, great. Yeah, I think that would be great. Just for the sake of time, I think I'm going to turn it back over to Dr. Wood. So thank you so much, Paul. Fascinating stuff. I honestly hadn't thought a lot about other worlds having oceans, so it's really interesting to see what research is being done. But of course, we have all of this research again has to start from where we are, our home planet as our original ocean world that we know of. So I'm going to turn it over to Dr. Michael Wood to talk about some of his research in Greenland.
Yeah, thanks, Claire. Let me go ahead and share my screen. All right, can you all see my slides?
Yes.
All right, great. So it was really cool to hear about all that exploration that's going on in the solar system in terms of the ice in the ocean. And I'm excited to be able to talk about exploration here on Earth at the edge of the ice in the ocean. And particularly, I'm going to be talking about some science that we've been doing in Greenland over the past several years. So I'll introduce a little bit what I do in a second. But before I do that, I wanted to introduce the Greenland Ice Sheet, which is really going to be the star of the show today. So the Greenland Ice Sheet is in the mostly in the Arctic Circle, and if you traveled up the east coast of the US and Canada, you'd find it up there. And I like to think about Greenland as sort of the Pluto of islands, because it just wasn't quite big enough to make the cut to be a continent, but it is, so it's sort of the next biggest island that we have on planet Earth. And one of the special things about Greenland is it's almost completely covered in ice. That ice is really thick. So in the center, it's more than a mile thick. We can quantify that in terms of volume. So we can say that it has 30 million cubic kilometers of ice. Or if we think about that in terms of sea level rise, that would be approximately 25 feet if the whole thing melted. So there's a lot of ice on the interior of Greenland, and in this talk today, we're going to be thinking about what happens at the edges. So at the edges of the ice sheet, Greenland has hundreds of glaciers. So you can think about a glacier as a river of ice, and these rivers of ice are constantly transporting ice from the center of the ice sheet outward toward the ocean. So in this photo that I took, the ice sheet is back sort of in the mist, and then the ice is flowing outward here and meeting the ocean. And when the ice meets the ocean, every now and then the glacier will break off large chunks, which we call icebergs, and you can see one of those here on the right side of my photo. So by Greenland standards, this is a pretty small glacier, and you can tell that because you can see most of the ocean in front of it. The really big ones, like say this one in Southeast Greenland, are putting out so much ice that sometimes it's even hard to tell where the actual ocean is. So it's this interface between the ocean and ice that is really going to be the topic of what I'm talking about today. So who am I? I'm what's called a postdoctoral researcher at NASA's Jet Propulsion Laboratory, which means that I've recently earned my PhD, and now I'm continuing a lot of that research at JPL. I study glaciers and why they're melting, and I also study the oceans and how they're changing, and in particular how the oceans and ice are interacting together. So I use satellite observations and state-of-the-art ocean models But in the summer times, I also go to Greenland and I do field measurements myself. So, and it's some of these recent field measurements that that are going to be the core of this talk. As far as that field work goes, I've done a lot of different types. I've worked on boats around Greenland, such as the Cape Race, which you can see in the upper left corner. That was in 2015. I've camped at the edge of the ice through the summer doing measurements on how glaciers break off ice. And more recently with NASA, I've been a part of an airborne campaign, which I'll introduce in a little while. And we've been using aircraft like the one you can see on the right-hand side to do measurements around Greenland. So in this talk, I'm gonna try to answer a few overarching questions. Why am I personally doing research in Greenland? What motivates me? Why is NASA doing this field work in Greenland? We normally think about NASA as doing some of the research that Paul was mentioning, thinking about the solar system or sending astronauts to the moon, things like that. And then finally, I wanted to touch quickly on some of the things that we've learned in Greenland from the field work that we've done. So why am I doing research in Greenland? Well, I grew up in Southern California, not too far from where JPL is located. And occasionally my parents would take me to the beach, such as Seal Beach, which is shown in this image. So here we're looking at Seal Beach through what's called the Sea Level Rise Viewer. It's a tool that is put together by the National Oceanic and Atmospheric Association. And I think the link will be dropped in the chat. And you can zoom in on portions of the US coastline and investigate what those coastlines will look like under various sea level rise scenarios. So here I'm showing Seal Beach under a 6-foot sea level rise scenario. You can see in the bar on the left. And what you can see here is that under this scenario at higher tides, a lot of the infrastructure that is currently in Seal Beach is going to be having issues with water encroaching onto land under those scenarios. So this is an issue that's sort of near and dear to my heart growing up in these areas. So I'm going to try to ravel back in the next few slides the connections between sea level rise and what's going on in Greenland. So like many things in our changing climate, sea level rise is linked with increasing CO2 concentrations. So here I'm showing on the left the CO2 concentration increase from about 1993 until nearly present day. And then similarly, the increase in global sea level as measured by NASA's satellites. And these curves, of course, look very similar. We can even put them on the same plot. And, you know, with some wiggles between the seasons, by and large, these curves match up pretty well. And so, of course, when curves match pretty well, we say that those two variables are correlated. And as scientists, we want to know what are the possible causes behind that relationship. So one thing you can do is go and try to create a budget of what is causing sea level to rise. So if you look at the total sea level rise, say in the past 21 years since the year 2000, we've got about 63 millimeters of global sea level rise. And it turns out that sea level is rising from two main processes. One we call barystatic, which is just the changes in the amount of water in the ocean. So of course, melting ice from Greenland ends up in the ocean, and that will raise sea level rise. But there's also an interesting unexpected cause for sea level rise, which we call steric. And this occurs just based on changes in the salt, the amount of salt or heat that's in the ocean. So we know that when you add heat to things, they expand. And that's actually a significant portion of global sea level as well. So as the oceans warm up, they expand, and that raises the water level a little bit. So today we're going to be thinking about ice, as I mentioned. So we can think about this barystatic component, and we can break that down into what's being added to the ocean. And what we can see here is since the year 2000, the Greenland Ice Sheet is adding a substantial amount of ice into the ocean. So causing the global ocean to rise by about 13 millimeters since then. And so this gives a lot of motivation to study what's going on in Greenland. But I'll mention that there are lots of other scientists working on these other processes, both at NASA and at other institutions. So why is Greenland losing its ice? Well, we can get a sense of that by considering where Greenland is losing its ice. And one way we can do that is by using two NASA satellites called ICESat and ICESat-2. Both of these satellites are equipped with lasers that are capable of measuring the height of the ice in Greenland. And we can track differences in the height of the ice through time. And what we primarily see is that Greenland is really losing most of its ice along the coastline. So we're seeing significant declines in the elevation of the ice around Greenland, and this is just very partially offset by, excuse me, a little bit of extra snowfall that's happening on the interior. So what's going on the coast? Well, it turns out that Greenland loses ice in two different ways. The first way is sort of the obvious way. On its surface, Greenland loses its ice just like an ice cube outside on a hot day. So if we have increases in air temperature, that's going to cause more melt. And we can look at the spatial distribution of that through time. So I've put together a little simulation from some model data that we have. And if we look at the net snowfall and net melt throughout the years, what we see is in the summertime, we have a lot of melt that's on the surface of the ice sheet near the coastline. So this happens because the edges of the ice sheet are at lower elevation, and air temperatures over the past several decades have been warming up, and so we're seeing more melt on the edges of the ice sheet. So that's one part of the story, but it turns out that Greenland is a little more complicated than just an ice cube sitting outside on a hot day. So it turns out, and we can use a different class of satellites to measure Greenland from space. And what we see is that the ice in Greenland is sort of constantly on the move, and it's flowing from the interior of the ice sheet out toward the exterior. So on the interior of the ice sheet, we have very slow ice, which you can see in those brown and yellow colors. And then as it gets closer to the coastline, it organizes into those glaciers, which you can see are faster flowing and are shown in those blue and pink colors there. So one thing to notice about where those blue and pink colors are, where the ice is flowing the fastest, is that that's where the ice sheet is actually in contact with the ocean. And this brings us to the second way that Greenland can lose its ice. It's that the glaciers in Greenland over the past few decades have actually been flowing faster and adding even more ice into the ocean. So this brings us to the second way that the glaciers are causing sea level rise. They're just simply adding more of the icebergs that they have each year into the ocean. So why is this happening? Well, this sort of links to why NASA is going to Greenland and doing field work. So NASA scientists have been, and others as well, have been looking at these faster flowing glaciers, and they started to generate this hypothesis that potentially the waters around Greenland were warming up and causing the glaciers to melt and flow faster. But we had a few problems in that we were missing some of the data we needed to test this hypothesis. Specifically, we didn't know what the ocean floor looked like around Greenland. And this is important because it tells us whether the glaciers just have their little pinky toe in the water or whether they're totally submerged in a big bath of warm water. And speaking of water, we also didn't know how the temperatures varied in space and time around Greenland. And the real kicker, NASA would like to view things from space. NASA is very good at putting together satellites and measuring things globally. But you can't see these parameters from space. You can only see a little bit down into the ocean. So it's very difficult to map the ocean floor that way. And you also can't see the deeper ocean temperatures because from satellites, you can really just see the surface. So this was how the Oceans Melting Greenland mission was born, or OMG for short. So OMG is a recent mission that ran from about 2015 until just last year. And we've had a few objectives with OMG. The first objective, quite straightforward, is just to measure the ice and ocean together and ask how is the ice changing and how is the temperature of the water changing, and can we see a comparison here? And the way that we've done that is to use aircraft around Greenland to get a pan-Greenland view of how these changes are happening year to year. So this is why we're using aircraft. And you can see one example of our flight tracks, which we did in 2020. And you can see, by and large, they're over the ocean where we're deploying instruments and trying to understand how the waters are changing. The second thing that we aimed to do was to map the ocean floor around Greenland, because we needed to know how deep that water was. Again, do these glaciers just have their pinky toes in the water, or are they sitting in a big warm water bath? And this was, I showed this picture of the boat that I was working on back in 2015. And now this gives a little bit of context to why we're doing these sort of in situ observations. So what have we learned from our work in Greenland? Well, all of the data that we've captured is really been a treasure trove, and we've been learning a lot, but I wanted to highlight one of the biggest things that we've seen in Greenland. First, we'll think about how the ocean temperature varies. So on the right-hand side, all of these yellow dots demonstrate where we've got instruments deployed around Greenland, and we can look at just one of those dots and zoom in on it and see what the ocean temperature looks like. So this is sort of a strange plot, but I can walk through a little bit. So on the x-axis here, we have temperature in degrees Celsius. On the y-axis, we have depth. And the way to think about it is if you were to dive down through the ocean column, what temperature would you be feeling as you went deeper and deeper into the ocean? So if you start at the surface and go down, you're fairly warm at 4 degrees. And then very quickly, the water cools down. So it gets to almost 0 degrees Celsius. So if this was fresh water, it would be nearly frozen. And this is analogous to if you've ever gone swimming in a lake and dove down a little deeper. The surface of the water is warm, you dive down, and then it gets colder. But something very strange happens in Greenland. As you dive deeper and deeper, actually, the water starts to warm up again. So from this 50-meter mark down hundreds of meters down, we get to a temperature which is nearly back to what the surface was. So what we see is we have a cold layer on top of a warm layer, and that's something very different compared to what we see in the global ocean. So we'll put a pin in that for 1 second and then think about what the ocean floor looks like, and then we'll bring them together. Here I'm showing an old map of what the ocean floor around Greenland looked like. So on the left-hand side, we have the ocean, where I've colored the ocean depth in blue. On the right-hand side, we have the ice sheet, and I've put red dots everywhere where we have the glaciers. And what you can see based on that white color that's in the ocean is that the water depth is quite shallow next to all of the glaciers in Greenland. So that's the old map. We can compare that to the new map, and in this coastal area where we've done all this mapping, now we can see a whole lot more detail. So we can zoom into just one part of this coastline in Greenland, and what we see is that we have a lot of channels now that connect the outer ocean in toward the glaciers, such as this one here. So these channels are upwards of 1,000 meters deep. If you've ever been, say, to Yosemite National Park in California, each one of these channels is like Yosemite National Park, but underwater. So we can now link this back to the ocean water temperature and think about how this is all affecting the glaciers. So what we know from the boats is that these glaciers are hundreds of meters deep down in the ocean. And what we know from the water temperature measurements is that the warm water is primarily at the bottom. So these two things combine to really cause the greatest melt at the base of the glacier, which is responsible for most of its stability. So as the ocean waters warm up, this is causing more melt, and this essentially takes the rug out from underneath the glaciers and allows them to flow faster. So now we're bringing it back around, and we can start to understand this relationship between carbon dioxide and sea level rise. So as carbon dioxide emissions increase, this traps extra heat in our planet, and a lot of that gets trapped in the ocean, causing the water to warm up. As we've seen, that contributes to glacier melt, and as glaciers melt from underneath, then they speed up, they dump more ice into the ocean, and then that causes sea level rise. So our next big question, now that we're armed with this information, is to try to think about the future. What is sea level rise going to look like in the future? Is Seal Beach, the area that I showed before, is it going to be subject to, say, 2 feet of sea level rise, in which the impact on current infrastructure is quite small? Or is it going to be more like 6 feet of sea level rise, and we're going to see a bigger impact on the infrastructure there? So this brings me to the end of my talk and some take-home messages. The main takeaway really is that more carbon dioxide, we can link more carbon dioxide in the atmosphere to more melt from the glaciers. But remember, not just like an ice cube outside on a hot day. There's this extra way that this happens by influencing the speed of the glaciers. So what we see is that warmer ocean waters are actually melting Greenland from below, just as warmer air is melting it from the top. We're thinking about next what's going to happen in sea level with sea level rise in the future, and helping us to be better prepared for that. And with that, I'll end and take any questions.
Great, thank you so much. We do have a couple questions in the chat here. Julie is asking if there's a great deal of geothermal activity in Greenland.
Geothermal activity. There is some geothermal activity that is under the ice sheet, but it's quite small, and what we can tell is that it's not varying by and large very greatly, and it's not impacting a lot of the glacier flow.
Great. And another question, do the channels also contribute more surface area to be warmed by water and cause greater melts?
The channels also contribute more surface area to water and greater melt. So I think by channels, potentially these are this question is referring to these channels that are here in the ocean. Yeah, so the deeper that the channel is, the more of that glacier can be in contact with the warmer water. And in fact, that's what we've seen, is that the bigger, deeper glaciers are actually experiencing more melt and more changes than the smaller glaciers, which are just in contact. The smaller, shallower glaciers are just in contact with that colder layer that's on the top, and the bigger ones, with the surface area and the warmer water are changing more.
Another question, what's next now that the OMG, what's next with OMG?
So OMG just wrapped up our last field season. So we are completely inundated with data now, and we're still digging through a lot of it and learning a lot from it. But behind the scenes, I think our OMG team is starting to consider looking at the southern ice sheet, Antarctica, because Antarctica will be likely subject to some of the same changes, but it also faces a lot of the same barriers. Namely, we don't know exactly what the ocean floor looks like around Antarctica, and in an Antarctic-wide sense, we could do a lot better in understanding what the structure of the ocean looks like.
Great. And another question, what are some ways we can mitigate our contributions to the problem? Is there any way in being proactive in helping to form a solution?
Yeah, well, I would say for by and large for climate change in general, we should try to get our carbon emissions to be a bit lower. And so this, of course, has to do with solar energy and wind energy and things like that. So I would say potentially a big focus should be those carbon emissions.
Great, thank you. One other plug for an activity on that link bank that Beatrice has put in the chat. There's an activity called Polar Bears Go with the Flows, and it's an interactive activity. where patrons work together on a game through a bunch of discussion questions about what we can do on a personal level to reduce our carbon emissions. So definitely check that out on the link bank if you are interested in tying some of this research into an interactive activity with your patrons. And we do have another question. Are there polar bears in Greenland? And are you seeing an impact on habitat?
So first part of that question, indeed, there are polar bears in Greenland. And I have a photo here that was captured on one of the boats that I was working on. And the impact on their habitat is certainly something that that's under active investigation. So that the polar bears do use ice flows, whether it's sea ice or broken icebergs, like you can see here, to hunt. And part of what we're investigating is whether the changes that we're seeing in the ice are affecting the polar bear's habitat. So stay tuned for that research.
And a personal question for your personal experience. What is it like to camp in Greenland in the summer, and how cold does it get?
Yeah, so Greenland, I can bring back this this photo that I took from our campsite. In the summertime in Greenland, there's 24 hours of daylight, so you can get a lot of work done, and it can be very pretty. In this photo I took here, it was a very beautiful day where this is sort of in the middle of the night where the sun is lower on the horizon. But when the weather's nice, it can be totally awesome. But when the weather's bad, like when it's raining or snowing consistently, and you're not only trying to do the things to take care of yourself, like cooking and things like that, but also taking care of the instruments. Like we have a generator to run. Maybe you can see the instrument that we have here in the background. Those require power. So when the weather's bad, the instruments are unhappy. We're unhappy because we're out in the rain and snow trying to keep things going. And so there's pluses and minuses, but certainly I wouldn't trade it for anything. It's a great time.
Great, thank you. Well, thanks to both Paul and Mike for being with us here today to share what they're doing this beautiful world and the beautiful solar system as well. So I really appreciate both of you being here and sharing your research. And thanks everyone for joining us today. When you exit out of here, there will be a short survey for you to fill out. So we'd appreciate if you could do that if you have the time. Also, Beatrice has dropped a certificate of attendance in the chat as well, if you would like a record of your professional development here. Yeah, I hope everyone has a really great day. And yes, I'll repeat Celine's comment. Thank you all for taking time out of your busy days for us. We know both of you are up to a lot of really important work, so we really appreciate this time spent with us. So thanks. All right.
Thanks to all of you. It was great to be a part of this. Yeah, so thanks for organizing, Claire.
Yeah, absolutely. Right. Have a great day, everybody.